All right, so our next speaker is DeClerk from University of Nebraska-Lincoln, and he will tell us about the falsification by fellow traveler property implies autostackability.
Yep. So basically half of this talk is going to be definitions of the stuff that's in the title, and then the other half of the talk is going to be proving the stuff that's in the title. So let's start off with some definitions. And we're going to start with falsification by fellow traveler property. So this was introduced by Neumann and Shapiro. And I believe that was in 94. I'm just going to check my notes. Yes, 94. So falsification by fellow traveler property. We have a pair of a group and a generating set. And this pair is going to have the falsification by fellow traveler property if there is some global constant k, such that whenever you have a non-geodesic word v, there is some u which is equal in the group to v, with the length of u is smaller than the length of v, and the distance between n steps along u and n steps along v is smaller than your global constant k for all natural numbers n. And this really wants an example to look at. So here I've got the same group with two different generating sets. So we've got z squared semi-direct z mod 2z. And over here on the left, I've got the standard 3 generating set. And if we say that this point right here is our identity, and we take some sort of inefficient path. So let's say that we take C, A, B, B, B. Sorry. Yes, that's correct. C. So C, A, B, 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 C. Well, we can get a slight improvement of that by taking this blue path instead, which is going to be just B, 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 A. And at every point, at every time, if you move one step along the pink path and one step along the blue path, so let's go to here and here, the distance between those 2 points is going to be 2. And likewise, if we go 3 steps along and 1, 2, 3 steps along, also distance 2. So with this generating set, we've got falsification by fellow traveler property. If we have some sort of inefficient path, we can always get a slightly better path, some slight improvement that is going to stay pretty close to our original. On the other hand, if we look at a different generating set, which is just A and C, so we're dropping the B's, we're dropping the purple edges, then here, if we do C, A, C, A, C, so that is actually equal in our group to A cubed, C, A cubed. So that's A, C, A. But it turns out that there isn't going to be any sort of intermediate way to get from the pink path to the blue path that is sort of staying close to the pink path. So the pink path is inefficient, but there's not really a way to make it more efficient while staying close to the pink path. And of course, I'm just using 3s here because that's what I've drawn, but you can throw n's in there and you end up with a linear bound between for how close two paths can be, or how close an improvement can be, versus the constant bound that you need for FFTP. All right. So FFTP is actually a pretty common property among nice groups. So there are lots of very nice classes of groups with FFTP, at least for some generating set. In particular, Neumann and Shapiro showed that geometrically finite hyperbolic groups all have FFTP for some generating set. Noskov showed that groups acting nicely on nice cat0 cube complexes, and also Coxeter groups have FFTP for certain generating sets. Holt got Garside groups, and Holt and Reese got Artin groups of large type. So lots of these classes of groups that we're really interested in that are really useful, really nice to study. They have FFTP for some generating set, though not necessarily all generating sets. All right, so that's one part of the title. The other part of the title is autostackability. So an autostackable structure for a group G with monoid generating set A, we're going to have a spanning tree T of the Cayley graph, along with a flow function phi. So this goes from edges in our Cayley graph to paths in our Cayley graph. And it has to satisfy 5 things. So first, our flow function takes an edge to a path with the same endpoints. So phi of E has the same endpoints as E itself. Second, there's some global bound K such that all of the paths that we get out of this flow function have length at most K. Third, for all of the edges on your spanning tree, the flow function leaves those edges fixed, so phi of E is just E itself. Fourth, there isn't going to be some infinite sequence of edges, E1, E2, etc., where EI is distinct from EI plus 1, and EI plus 1 is an edge in the path phi of EI. So basically, this is a termination condition. You don't want to be able to apply the flow function forever and ever. And then fifth is a language theoretic condition. So the set of triples, normal form of an element, followed by a letter, followed by the label of the path phi of E is going to be a regular language. And this really desperately wants an example. So we're going to go with BS12 as our example. So we're going with generating set A inverse, T inverse. If you aren't familiar with BS12, AT as your generators, and AT inverse is A squared. So the tree of normal forms is just going to be T to a negative power, A to a power, T to a positive power, where either I times K is 0 or J is odd. And then the flow function is a little bit complex, and I don't really want to go through all the details. So what I'm going to do is I'm actually going to just show you a picture. So here's the Cayley graph for BS12, or at least a fragment of the Cayley graph. So the green edges are going to be your spanning tree. These are going to be the normal forms of your group elements. And then the black edges are the things that actually get rewritten. So if we look at this black edge over here, well, what's going to happen, we are going to rewrite that to this edge, like so, or this path, like so. So instead of going up along this black edge, we are going to backtrack basically along the spanning tree. And if you look at something, let's do a different color, like here, we're going to do basically the same thing. So instead of going directly up, we are going to decide to backtrack, go up, and go forwards. And I actually backtracked a little bit too much there. And the reason that we aren't going all the way to the actual spanning tree, and we aren't following the spanning tree for the entire path, is because we want to have some boundedness. So the length of the path in this case is going to be bounded above by 5 edges. All right. And of course, we can do something similar for edges like this one. We're just going to go down over up. All right. So why do we care about autostackability? Part of the reason is because it generalizes a couple of very nice structures that are already well studied. So it generalizes automatic structures and it generalizes finite convergent rewriting systems. And both of these are nice ways to solve the word problem for certain groups. And autostackability, you do the same basic thing. So you can solve the word problem using autostackability. Basically, what you do is you repeatedly apply the flow function to whatever word you're trying to find the normal form of. And the regular language part of the definition for autostackability, that's basically just to make sure everything is nice and computable. All right. So that's both of the big definitions I needed to talk about. And now we can get to the big theorem. So, theorem, suppose we have a pair GA with falsification by fellow traveler property, and we've got some fellow traveler constant K. Then G is autostackable with short reverse Lex normal forms. And short reverse Lex normal forms, basically think about it as short Lex, except you are reading right to left instead of left to right. I'm not going to give you the full detailed proof because honestly, that's like 5 or 6 pages. So I'm just going to give you an outline of the proof. So we've got 3 basic things going on. First, we need to make a flow function phi. So we need to decide where do each of our edges go. Second, we need to show that we get termination. So back when we were defining autostackability, we had this 4th point right here. So we have no infinite sequence of edges where basically you can apply the flow function forever and ever and keep getting different things. So we need to avoid that. We need to have this sort of termination condition. That's going to be the second thing we prove. And then the third thing we need to prove is going to be regularity. And that is basically we're going to be using closure properties of regular languages. So if anyone here works a lot with finite convergent rewriting systems, you are going to be very comfortable with, okay, we need to show termination sort of things. If anyone works a lot with automatic structures, then you're going to be very comfortable with, okay, we need to show regularity sort of things. And autostackability, you kind of need to do both. So, all right. So, first thing to do is make our flow function. So this is a nice little fact that we can draw a nice picture for. Every word U which is not short reverse Lex normal form of a group element is going to 2k fellow travel a short reverse Lex improvement. And this is actually pretty quick to show. Do I want to do that? Not really. Let's do that. So we've got some word u, which I'm going to do in purple. We've got the normal form of u in green. And they might share a common tail, but because u is not the short reverse Lex normal form, we know that there's going to be some difference. And we're going to look at the sort of last edge along that difference. So what can we do? We can say, let's find a nice path from the identity to this point, to basically u up to this common boundary, followed by the last edge of the normal form reversed. And we know that we can find a length improvement that is going to be within k. So at each step here, u is going to k fellow travel. We're going to call this u1. Actually, let's call this v1. And maybe v1 has exactly the length that we need. Maybe the length of v1 is exactly the length from between these two blue points. But it might be that length plus 1. So in that case, we might need to apply our FFTP assumption a second time. Anyway, so V is going to be our short reverse Lex improvement. All right. Anyway, we're going to use that fact to define our flow function. So when we've got a group element G and some letter A, where the normal form of G followed by A is not genuinely a normal form, well, we know that there is some V that is a short reverse Lex improvement that is going to 2k fellow travel. And we are going to define our flow function in 2 parts. So part 1, if u is sufficiently short, then we just rewrite u directly to the normal form. So what we do is we say, we've got u along here, we've got a along here, we've got normal form of ua along the bottom. We're just going to say a rewrites to, or we're going to say the flow function sends that edge labeled by a to this pink path. And that's fine, that's great. Everything's wonderful, but that's only going to happen for sufficiently short u's. So for longer u's, what we do is we define a few things. So we define u1, u2, v1, and v2. So that u1, u2a is equal to u. So u1, u2 is the group element that we started with. v1, v2 is equal to v. Size of u2 is k plus 1, and size of v1 is size of v1. And then what are we going to send that edge a to? We're going to backtrack along u2. We are going to take the normal form of u2a v2 inverse, and then we are going to go forward along v2. So this really wants a nice picture. So we've got our identity here. So we're going to take U1, U2, A. That's not what I wanted to do. V1, V2. And what we do is we, instead of taking this A edge, we go backwards along U2. We cross a bridge over here. And the length of this bridge we know is less than or equal to 2K because U and V are going to 2K fellow travel. And then we go forward along V2. And again, the reason that we don't want to go all the way back to the identity and then go forward along V1 and V2 is because we need some boundedness. So basically, we stop right here for the sake of boundedness. All right. So we have defined our flow function. Now we need to define termination, or sorry, now we need to prove that we've got termination and we need to prove that we've got regular languages. So termination is actually pretty straightforward. So whenever we've got this edge A that we are actually applying our flow function to, essentially what's going on is we are moving a flaw in our word to earlier in the word. So, and what's actually happening is all of the edges along this pink path, they are closer to the identity, with the possible exception of that red is not showing up very nicely against that pink. With the possible exception of the very last edge along V2. So the very last edge along V2 might be the same distance as this A edge that we started with, but it's going to be lexicographically smaller. So that's basically what this is saying. If we have some edge E prime that is in our path phi of E sub GA, either E prime is closer to the identity than the original edge that we started with, or E prime is the same distance from the identity and it's labeled by a smaller letter. So we got some nice well-foundedness from there, basically. Regularity is a bit trickier. And in fact, what I'm going to say is there is a nice language that we can prove is regular. In particular, it is this language, all the pairs UV, where U is equal to V, U and V 2K fellow travel, and U is larger than V under short reverse lex order. So we know that that's regular, or we can prove that it is. And we can manipulate that language using a variety of tools that maintain regularity. So regularity happens to be closed under a lot of really nice ways to manipulate languages. And I am not going to go through all the details. All right. So that was the main result. And I'm going to briefly mention this related result. So we can use a very similar flow function construction to show that any group with a length non-increasing regular convergent prefix rewriting system is autostackable. So what does that mean? It basically means you have some set of rules to rewrite words. Let's say all of those rules are left goes to right. where the set, all of these words, or all of these pairs, LR, is regular. The size of R is smaller or equal to the size of L. And there's a couple of other conditions. I'm just gonna sweep those under the rug and say a couple of other conditions. Termination and unique normal forms are the two big ones. So, and this is a slightly more powerful result, in particular, the example up here, a little bit farther up. This example up here that does not have FFTP, that is covered by this slightly broader theorem. So. All right. And I'll end it there. Thanks for listening.
All right, let's thanks the speaker. Okay, so we still have a bit of time. Any quick questions?
Do you know about any autostackable groups that doesn't have the property FFTP?
Oh yeah, there are plenty of autostackable groups without that property. So BS12, which I mentioned earlier, autostackable but does not have FFTP. FFTP is actually very restrictive. In particular, FFTP implies quadratic Dane function and I believe it implies some homological conditions, but I'm not 100% confident on that. I am not the expert on FFTP groups.
Yeah, it implies FP3 or type F3.
And F3. Okay. Okay, yes. All right, so FFTP implies a quadratic Dane function and homological type F3. And there are examples of autostackable groups with power towers for their Dane functions. And there is one which I know is finally presented, but not FP3. I'm not sure if it's F3 or not. But yeah, there are plenty of examples of autostackable groups which do not have FFTP.
Okay, thank you.
Yeah, Murray.
Hi, Ash. Yeah, the proof, I think I've asked this before, the proof in parts looks like you could maybe get away with almost convexity as a hypothesis.
Almost convexity.
Imply autostackable.
Yes. So you can almost get away with it. The problem is regularity there.
Okay.
And one of my fellow grad students at UNL and I have been trying to get some stuff with almost convexity and a weaker version of autostackable, but it's a bit tricky. There is one thing that's known. So almost convex implies algorithmically stackable. Which basically you remove the regularity condition and replace it by recursive. So the set of languages, or the set of rules that you get, is a recursive language. But that is recursive is way, way weaker than regular, obviously. So
there's a lot of languages in between, I guess.
Yes, quite a few. I think, do not quote me on this because I don't have a proof, but I think we can recursive to context sensitive potentially, but it's going to be very tricky.
Cool. All right, I think we should stop here. Arman is restless, I can see. So, all right, let me make you the co-host. Oh, I should stop recording.